Okay, great. Thank you very much for giving me the opportunity to speak here. Thank you very much for being here. In this talk, I'll try to continue the research program that David advertised in the last talk and elaborate a bit on that and about newer perspectives and new challenges that we managed to solve over the last couple of years. And maybe to just connect it with what you heard before the coffee break, is David gave you some very nice convex reconstruction guarantees, and at the heart of it was actually this matrix Bernstein inequality. This was also treated in the questions, but a very important caveat, a technical caveat with this matrix Bernstein inequality is that it doesn't only require a matrix valued variance, but it also requires regularity conditions. And David mentioned this in his talk when he excluded pathological examples. So kind of one of the underlying assumptions in David's approach was that kind of the trace inner product between the measurements that you use and any signal that you wish to recover has to be small. And this is really important. And it worked nice in David's approach because he just assumed that like the eigenbasis of the signal he tried to recover is somehow unbiased or like has a lot, is the class itself, or alternatively use the Pauli measurements. Now in this talk, I want to talk much more about phase retrieval, this spin-off problem that David mentioned in the end, and that the situation is very different. Because remember, there was this lifting trick that allowed to lift these quadratic constraints onto linear measurements on two rank 1 projectors. One of them being the rank 1 projector onto the signal that you wish to find, and the other one being the rank 1 projector associated with the measurement. Now these regularity conditions, it's easy to see, can never hold if both of the objects are rank 1. Because if this were a rank 1 matrix, and I need this to be true for any kind of measurement, any rank 1 projector X, I can maximize over it, and in the end I get something that is very big, that is not small. So we really had to like kind of develop new technicalities to treat this problem. I don't want to go into depth about it, but just to start my talk with somehow trying to justify that there was still a lot of work to be done. And with this, I actually want to start, and here's the outline of my talk. I first want to talk a lot about candidates of potential measurements for phase retrieval, because as I mentioned before, like these kind of nice Pauli measurements or basis measurements, they don't apply to phase retrieval. So we need new candidates, nice measurements. And then I will take time to actually introduce them, and then I will actually present a result that is pretty strong, and it kind of tells you that these measurements that we found are optimal at the task of retrieving phases. And then actually we'll do a jump that might seem quite surprising to many of you, but on a technical level it's very, very intuitive. And actually the results on phase retrieval that we found allow us to like relatively straightforward also treat a very important case in quantum process tomography, namely optimal channel tomography of unitary gates, where we use average gate fidelities as measurements. And this is conceptually very related. And recently we managed to put on the preprint server where we showed some strong results there. And if I have time in the end, I actually want to come to another incarnation of this research project, which is about distinguishability of quantum states and coins. So without further ado, let me pick up with the motivation. And the motivation is, again, David before mentioned there's this phase retrieval problem that received a lot of attention in the literature over the last couple of years. And one of the first strong reconstruction guarantees were, again, by some people of the West Coast, and they could show that random Gaussian vectors as measurements perform essentially optimal. But this is not so interesting for applications because it's very, very difficult to implement them. So we kind of look for candidate vectors that kind of allow us to replace Gaussian vectors with some other ensemble that has more structure, but is still random enough to kind of allow for proof techniques. So we are looking for candidate vector families that are generic enough to facilitate these randomized proof techniques that are a bit more difficult, actually, than the ones David mentioned. But at the same time, we want them to be like somehow structured enough to be relevant. Like if we just allow for generic measurements, is not very realistic. And the ansatz that we pursued there is to look at orbits of certain finite groups, because they are still like kind of generic, also have a lot of structure. And we don't only look at arbitrary groups, but we look at stabilizer states and orbits of the Clifford group. And so in the next couple of slides, I want to give 3 different flavors and introduction to stabilizer states. So stabilizer states usually are defined for power of 2 dimensions, and they form an orbit of the Clifford group, and they satisfy all these desiderata. This is the take-home message of the first talk. And this is just not some random group that we cooked up, but it has appeared independently, actually, in coding theory, in lattice theory, and time frequency analysis. And also stabilizer states, and more generally the Clifford group, are one of the central tools in quantum information theory, especially if you want to think about fault tolerance and quantum error correction. In quantum info, they are really prominent. And for those of you who like their Wigner functions, there are also discrete versions of complex Gaussian states defined in a continuous phase space. Okay. Here is an elementary approach on how to define these vectors. And recall, as a starting point, the Fourier basis associated with the finite field set 2 mod n. Then we can label in such a space, so if you have c to the power of 2n, we can label the standard basis actually by bit strings in that finite field. This is just a convention that in quantum info, we call that the computational basis. And then the associated Fourier basis to this set 2 to the power of n is uniquely defined by linear forms that map these finite fields onto itself. And kind of what happens is any Fourier vector is a flat vector, so this is just a normalization, 1 over the square root of the dimension, and then it's either +1 or -1, and whether it's +1 or -1 depends on a linear function on the computational basis vector that I input. So this is what Fourier vectors look like. And stabilizer states can be seen as a generalization, and the most obvious one, we replace this linear form in the exponent by a quadratic one. Again, by a quadratic binary form, it looks like this, exactly how you might expect, but the diagonal is somewhat trivial because we do arithmetic modulo 2. So we can just do this, and then we end up with a potentially much bigger family of vectors because quadratic forms includes linear forms, and is the archetypical example of a stabilizer state. I'm sweeping a bit under the carpet because the most general definition of a stabilizer state actually also requires you to choose an affine space inside there, a quadratic function, as I pointed out before, and a linear function that allows for phases that are proportional to the complex unit as well. But morally, this is really what you do. Instead of using linear functions that give rise to Fourier vectors, you use quadratic ones in the exponent. And this is an elementary approach that allows you to define all these sets. And the set of all stabilizer states is the set of all vectors that can be generated this way. Now, the second approach, that is the most popular one in quantum info, and actually probably the approach that most of us learned when we read Nielsen and Chuang. And the trick kind of for stabilizer states is that they have low complexity, but they live in an exponentially large vector space. Just specifying all the coefficients individually requires exponential storage. And so there's a trick to come around that and actually parameterize these vectors by just using order n squared many bits, which is a logarithmic improvement. And the starting point is to recall the Pauli group on C2, which is just these 4 matrices. And they form a group up to phases that I sweep under the carpet here. And you can extend this naturally to power of 2 dimensions, but just consider the group that is formed by tensor products of these elementary matrices. Okay? And then these polymatrices have a nice property because they either commute or anti-commute. And so you can define a stabilizer group to be a maximum subgroup of this bigger Pauli group that is also abelian. So all the elements commute of this group. And because all these elements commute, they have a common eigenbasis. You can diagonalize them all at the same time. And stabilizer states actually just form the joint +1 eigenvectors of their stabilizer generator. This is probably an indirect way, a more indirect way of defining these vectors, but it is extremely useful because, first of all, count how many stabilizer states you can get that way. And you can see it is it's super exponentially many, actually, in the dimension, super polynomially many, super exponential in n. But more importantly, it gives you an efficient description because you can write down generators for all these maximal abelian subgroups, and you just can specify the generators. And this allows you to specify every stabilizer state just using an order of n bits, exponentially many you would need to naively write them down. And this is closely related to a famous theorem in quantum information theory, which is called Gottesman-Nil. And you can kind of exploit this very, very efficient description to simulate circuits that only use stabilizer states efficiently. There's no quantum speed up when you try to do this because you can simulate it classically. And then there's also a symplectic connection and a more geometric approach on all this. And it's heavily based on the symmetry group of all stabilizer states. And so the Clifford group, CLN, in power in n qubits, so in dimension 2 to the n, is the group that maps Pauli matrices to Pauli matrices under conjugation. So it's a symmetry group. And interesting group is just essentially a representation of the discrete symplectic group over the finite field we talked on the first introduction slide. And it's related to the metaplectic representation in mathematical physics and the oscillator group in time frequency analysis. And here's a couple of useful facts. The stabilizer introduced in the last slide are in a one-to-one relation with Lagrangian subspaces of discrete phase space. So kind of you can discretize phase space, and then it allows you it's just C2n, O plus C2n, and you can label each Pauli matrix by a bit string morally inside here. A finite field, a phase space, and there's some natural symplectic geometry on it. Because there's a symplectic form that tells you if two Paulis commute or not. And so all these relations from the previous slide generalize here, and the Lagrangian subspace is just a maximal subspace that in the sense that all its elements, the symplectic inner product between all its elements vanishes. And Clifford group, acting on this Lagrangian subspace, is actually the symmetry group of these Lagrangian subspaces. So it maps Lagrangian subspaces onto Lagrangian subspaces, which in turn implies stabilizer states themselves form an orbit of the Clifford group. So the Clifford group is the symmetry group of all stabilizers. Okay, that's orbits that we are interested in. And very general motivation about randomized proof techniques in general, but it is also, keep in mind that I want to solve this phase retrieval problem that David introduced earlier. And we want to use a randomized proof technique to get by with as few measurements as possible. And randomized proof techniques, in general, require information about moments, because moments tell you how generic your situation is. And how can we get that? Well, stabilizer states, as I just mentioned, fit under the Clifford group. So if I want to compute moments, and a very general computing moments is just looking tensor products of these stabilizer states, and then averaging over all of them, then because they form an orbit of the Clifford group, this is the same as twirling over the entire group and starting with an arbitrary starting point in the orbit that is sometimes called a fiducial. But moments of this form rewritten like this. And well, we're here. We can just use Schur's lemma, one of the most basic result representation theory, because you can easily see that this expression on the top, which characterizes all moments, commutes with the k-fold tensor product of any Clifford itself, because you can squeeze it in from the left, then just relabel the summation and then pull it out on the right. And Schur's lemma tells you that if a matrix commutes with every element of your representation, then it has to be block diagonal with respect to the irreps. So this is a very basic result. And so the question of computing moments of stabilizer states on to finding irreducible representations of this k-fold tensor product of Cliffords. And of course, the Clifford group itself, subgroup of the full unitary group. And the unitary group itself is not irreducible anymore if you look at tensor products larger than 2. So the unitary group itself factorizes into certain blocks, but the Clifford group is a proper subgroup. So it will not have the same irreps in general, but it will decompose finer. But we can use representation theory to try to understand how it decomposes finer, and as soon as we do that, we know the moments of our random vectors. And so the moments are essentially fixed by simple representation theoretic data. Well, this all is nice on one slide, but just use Schur's lemma is quite a tough advice, because we've tried to do that actually since 2012. I mean, the Clifford group is not necessarily an easy group, and kind of we worked on a dual approach. So like, for one side, we tried to work out the representation theory for higher and higher moments of the Clifford group. So when we started in 2012, it was known that the Clifford group exactly reproduces the moments of the Haar measure for second moments. Beyond that, nothing was known. So at the same time, we tried to find randomized proof techniques and optimize them to get by with lower and lower moments. So kind of we started from two sides. Kind of we knew the first two moments of the Clifford group are nailed down, but we kind of in the beginning needed logarithmically many moments to make our proof work. And so between 2012 and 2016, we kind of approached the problem from two sides. And in a series of works, we could actually nail down the representation theory for the moments of the Clifford group up to order 4. And this gave us some room to play with, because now we had access to 4 moments. And at the same time, with a different set of authors, we really optimized the proof strategies associated with phase retrieval in particular now to get by 4 moments only. And so the two bounds matched in late 2016. And for me personally, this was an important date because this was 1 month before my PhD defense. Okay, so kind of this is the high-level picture of our approach, and I'm very, very happy that kind of we managed to nail down the app. And let me just now quickly jump to one of the results that I promised you. Like David was mentioning this phase retrieval problem, and he kind of told you that quite good results were found if you choose your measurement vectors randomly from a Gaussian distribution, so very generic. Now what we could prove is that phase retrieval can be done from an order of dimension times the log of the dimension random elements of any Clifford orbit. This includes stabilizer states. So up to an additional log factor, this is actually optimal, because you can convince yourself if you want to find an arbitrary d-dimensional vector, then this has d degrees of freedom and you can't hope to get by with fewer than d. Now, for Gaussian vectors, this was actually nailed down, and you actually really only need c times d many. But if you are willing to invest another log in the dimension, you can actually go back from very, very generic Gaussian vectors to stabilizer states, which have a lot of structure. And this actually extends to lower rank matrix recovery. So that was what David talked about. In phase retrieval, you're guaranteed that the matrix you're looking for is rank 1, but you can relax that. And yeah, well, construction can be made, this is just a technicality, but it can be made stable with respect to additive noise corruption. So kind of if your measurements are not perfect and you have some additive noise, this is stable. This is a benefit of using convex reconstruction techniques. And again, the punchline is the control of the first 4 moments yields an almost optimal result in this case. And more generally, the framework I tried to explain on the last slide, this entire approach provides a more general framework for analyzing measurement ensembles that have a group symmetry. And I strongly do believe that the Clifford group is not only the only example, but that nice measurement scenarios often have a group structure that can be analyzed. Okay, now here's just a slide with some numerics that kind of tells you that it really works well and that the number of measurements almost looks linear. I kind of like this. I kind of like this formula, this numerics table, because here we crank up the dimension of the problem, and here we allow for more and more measurements, and this is a phase transition plot that tells you the probability of correctly reconstructing. And it goes from black, nothing goes, to white, everything is recovered perfectly, and there's a very sharp phase transition. And the reason why I like this plot is this numerical, this red line is 4 times the dimension minus 4, which is very close to universal lower bound on the minimal number of measurements that you need in order to solve this phase retrieval problem. Michael Wolf and collaborators, I think in 2009, showed that the minimal number of measurements you actually need is 4 times the dimension minus the number of 2 in the binary expansion of the dimension. So, number 1s, yeah, sorry. Thank you. Number of 1s in the binary expansion, yes. Something very obscure. And let me now do a quick step. let's go back to quantum information theory, and in my opinion, one of the most important tasks to date, where our devices become bigger and bigger. And let us set us the following task. Let us try to unitary channels from average gate fidelities with respect to Clifford gates. I think this is a very, very reasonable research program, because arguably unitary channels are the most important channels that we wish to build in quantum architectures. Like all the quantum gates are unitary. And if we if we can recover them, if we can do full process tomography, we actually get actionable advice if we did something wrong, and we can start fine-tuning. And at the same time, I find using average gate fidelities as measurements pretty interesting, because there's randomized benchmarking. And randomized benchmarking gives you, in principle, spam-robust way to actually get these data points. And this is one of the big weaknesses of any traditional process tomography scheme or state tomography scheme, that if you don't know your measurements perfectly, then it is very, very unstable. But kind of using average gate fidelities instead, via randomized benchmarking, kind of allows you to bypass this fundamental drawback. And finally, well, average gate fidelity, well, Clifford gates, of course, because we want to use randomized benchmarking. And the Clifford gate group features naturally there. So it's kind of plausible that experimentalists will be able, or they actually are able, to actually compute average gate fidelities with respect to Clifford gates. So this looks very, very different to the phase retrieval problem that I just showed you before. But I just now want to convince you that it's actually not. It's actually really, really similar. And here is the textbook definition of the average gate fidelity between two channels. The idea is that you fit in a pure state, apply the channel T to it, then you apply the adjoint of the other channel to it, and in the end you measure the overlap or the survival probability with respect to where you started. The intuition is that if T and C were the same channel, then this should be the identity. And in the end, you just average over all possible input states. And this gives you the average gate fidelity. And again, there's protocols that allow you to reconstruct, to estimate this efficiently if one of the two channels has some structure. Now here's the magic formula. There's a fundamental relation between the average fidelity and entanglement fidelity, derived by the Horodetskis in 1999, and then re-derived by Nielsen in 2002 in a way that people like me actually understand. But crucial insight here is that this gate fidelity between two arbitrary states. Here's some, just don't pay attention to this, but this is the trace inner product between the two matrices. So kind of, you can actually view an average gate fidelity as a bell-type measurement on the Choi matrix of the state channel. So kind of, if you go to average gate fidelities, you can kind of do ancilla-assisted quantum process tomography without ancilla. And this is pretty cool. And again, if one of the channels is unitary, then I put it over the corresponding Choi matrix, maximally entangled state. So it's a rank 1 projector, very much like in phase retrieval. And if we later assume that the channel we wish to hunt for, which we recover, is also unitary, then this will also be a rank 1 projector. And we are exactly in the phase retrieval regime. But the geometry is a bit more complicated. If we actually settle down to measure average gate fidelities with respect to unitary gates, which is what we want to do, these matrices are not only rank 1 projectors, but they're also maximally entangled. So kind of there's some additional structure here. And now you can look at the affine hull of all such Choi matrices, and you will find out that it spans the affine space of all trace-preserving and unital maps. Yes? Yes. Well, let me assume that for technical reasons now, in the end what we get is we can show that with an optimal number of measurements, we can get the best unitary approximation to the actual channel. And so if they kind of do a bit of an over or under rotation, we kind of can detect that. But yeah, like all these possible measurements, all these Choi matrices span the affine space of trace-preserving and unitary channels. So if the unknown channel we are hunting for is not trace-preserving or unital, then it won't be in this affine space. And there will be directions that we don't see. And so with this approach, when you want to use average gate fidelities, then the best thing you can ever hope to do is to recover the unital part of a channel. Like you are not able to see, you're blind towards non-unital and leakage. And of course, like if you want to do that now, we've seen that like kind of all these tray matrices of all unitary channels kind of form a circle. But this circle, we don't have to measure the entire circle. Like if we're just interested in recovering unital trace preserving maps, then all we need is kind of a simplex inside there that is solid so that it spans the entire space. And this kind of gives you very natural conditions of how many measurements you actually need to reconstruct any unital and trace preserving channel. And this is an easy exercise in geometry. So this is just what I said. But the affine space itself, I mentioned these squared plus 1, and so you need this number plus 1 finely independent unitary gates with respect to which you measure your average fidelities, you reconstruct any unital channel T. But of course, the conditioning kind of, if you've done that, you can basically do linear inversion, but the conditioning depends a lot on which unitaries you choose. Like you can geometrically understand that like kind of if you put 2 or a couple of your unitaries close by, then like the simplex that you get will be like very, very narrow, and if you do linear inversion, you will not be stable. So kind of you want to put these measurements as far away from each other as possible to get a well-conditioned inversion in the map. And here's a fun result that we could show this year. The reconstruction is particularly nice if you choose unitaries on this, if you choose a subset of all possible unitaries such that the second moment, them randomly, the moments of the Haar distribution, like of all unitaries. If you do that, you get a really evenly spread set, and inversion becomes almost trivial. So kind of once you agree to do that, the formula for your channel is actually just the sum over all your elements, and all the coefficients are the average gate fidelities themselves minus a constant offset. So linear inversion doesn't get much nicer than this. But once you settle for this, you still need enough elements to span this entire affine space. So you need an order of d to the 4 many measurements. This is not surprising because this is the number of degrees of freedom in a general unital and trace preserving channel. But here, let us now divert and go back to the ideas that David mentioned before. Yes? Yes. Yes, actually we do. Kind of what this is, if this recovery is exact, if T is a unital and trace preserving channel, the problem arises if it's not. And then this is effectively a projection onto this affine subspace. So you really get, if you think in the Pauli-Liouville representation, like in this transfer matrix picture, then what you nail down here is like the first coefficient that tells you where the identity goes to, and the unital part. But kind of like these state-dependent leakage and non-unital contributions in the first row and first column will be set to 0. But this is really, in a precise sense, the closest trace-preserving and unital map that you can have with respect to your channel that is non-unital. But I'm happy to discuss more about that offline. Well, just choose a set of unitaries, such that if you randomly sample from them, you reproduce the first 2 moments of the Haar measure. And the Clifford group has this property. And there's like in special dimension, there's other finite families of unitaries, but in general, this is not an easy problem. But of course, you can also choose randomly, and then you will get it approximately right. Yes. But kind of, I actually don't want to talk about this. Andrew Scott did a lot of work on this, on precisely this topic 10 years ago. But I actually don't care about how many unitaries I have, because I will subsample. So kind of, I will choose randomly from a fixed set of unitaries, but only very few. So I actually don't really care how the set of unitaries is I started with. Let us go back to concept that David explained before. Well, unitary channels have Krauss rank 1, and therefore their Choi matrix has matrix rank 1. And so we are really, if we restrict our attention for unitary channels now, we are really in this phase retrieval picture. And because these average gate fidelities are also just the trace inner products of 2 rank 1 matrices. And this looks a lot like phase retrieval, and indeed, the techniques we developed kind of allow for doing that. The last essential insight and ingredient was that if we actually choose random unitary gates from the Clifford group, then their associated Joy matrices look a lot like stabilizer states. And here I'm sweeping kind of a lot of hard work in representation theory under the carpet, but in principle we knew what we had to do. Because I told you before, we nailed down the first 4 moments of the Clifford group, so we had the tools in principle to do that. Of course, it's another question to actually carry out these computations, and this was mainly done by Ingo Roth at the Free University of Berlin. But we basically had all the pieces in play. And yeah, this is the result. By now it shouldn't be too surprising for you. It only applies to power of 2 dimensions because we use the representation theoretic ideas from the Clifford group. It only applies there. And then if you actually sample a number of d squared times log d average gate fidelities with respect to random Cliffords, then you construct any unital channel or the best unitary approximation to your channel by solving a simple convex optimization problem. And just to connect this further to David's talk, you don't see a trace norm in here, but kind of this is a trace minimization problem in disguise, because our set of our feasible space is the set of all unital and trace preserving channels, and they all have trace norm 1. So kind of the trace norm minimization is superfluous, and so here what we actually do is just the least squares fit of the data with respect to the constraint that we actually have a unital quantum channel. And you can rephrase this as an SDP. And I think this is quite nice because it's almost a quadratic improvement towards the linear inversion technique I mentioned before, d squared many measurements for unitary channels. You can actually show that this procedure is sample optimal if you measure your average gate fidelity smartly. But if you choose randomized benchmarking to get your data points, which is more expensive, you actually become stable with respect to not knowing your measurement devices perfectly. Okay, here's some numerics that I shamelessly stole from one of the earlier papers that led to this result by Shelby Kimmel and others, where they actually do some numerics about how this works. So kind of they actually just take a random unitary channel and they try to recover it using these techniques. And they measure, here they choose random unitaries to measure average gate fidelities, and here they use Clifford unitaries to measure average gate fidelities. And the important thing is that you see here that there's hardly any difference. So the proof is much, much harder for the Clifford case than for the generic unitary case, but numerically they perform equally well. Okay, great. This gives me like roughly 12 minutes of time to talk about the funniest application we probably had. And let us play some game. So probably you're familiar with both of these figures from classical pop culture, and you probably know that both of them are rather sinister, and both of them have an obsession with coins. Now, as you probably know, one of them always tosses a fair coin to decide whether you live or die. Whereas the other one is a bit more sneaky, and he always tosses a coin, but it always comes up heads, so that he's always right. So let us consider the following hypothetical scenario of a game that, given the participants you really want to win, suppose that a third supervillain kind of the coin of this guy or the coin of this guy with equal probability hands it to you, and you are allowed to toss the coin once, and based on your outcome, you have to guess which coin you had obtained. So what's the optimal strategy? Again, like you receive both coins with equal probability. One of them always comes up heads. One of them is fair. Yes, if you get heads. Well, let's find out. So we can phrase this problem much more generally as the task of distinguishing classical probability distributions, and for the sake of simplicity, that they are discrete. And the rule of the game is that we're handed like the random variable associated with one of them with equal probability, and then we toss it once, and then we have to guess which probability distribution we got. And kind of the degree of freedom we have is that we can optimize over elementary events associated with outcomes. Like for coins, the event, and then there's event tails. And we can base our optimal strategy based on these events. And since probability distributions can always be represented as non-negative real vectors, this optimization problem is actually a linear program. Because kind of the evil guy is asking you about the question, like which coin did you get? And so there's only two outcomes. And so you can, without loss of general your strategy to find two events, one associated with coin 1 and one associated with coin 2. And then you can write down your best decision as a maximization problem. And it's just simple linear algebra that I use. That kind of, the second event has to be 1 minus the first event. This is actually just a maximization of a linear function for fixed P and Q over all possible events. And this is a linear program. And it's actually the nicest kind of linear program because it's possible to solve it analytically. I'm not going to do it here because I'm running out of time. But trust me, it's not so difficult. And in the end, you can see optimal probability of success is given by 1/2 plus 1/4 times the L1 distance between P and Q. And this is just the total variational distance and the reason why statisticians like it. Moreover, the optimal strategy is just the maximum likelihood rule from statistics. So given an outcome, you guess the coin that was most likely. So to come back to your idea, Marco Tullia, from before, you were totally right. Like tails, if you get tails, then you say it was the fair coin because there was no way that the other coin could have led to that. This is the maximum likelihood rule. But conversely, if you get heads, like one of the coins gives heads with probability 1 and the other one only with 1/2. So the maximum likelihood rule would actually tell you that you would then get this is the optimal strategy. And just to come back to the game before, like by following this strategy, you have a success probability of 3/4. Okay, now you can play this, the quantum version of this game. Now we have again a binary question, like some referee hands one of two quantum states. You know the density operators of both. This is the rule of the game with equal probability. Then you have to guess with the single quantum measurements which state you obtained. Again, this is a two-outcome question, so you can optimize your strategy over all possible two-outcome measurements. And if you do that, well, you don't get a linear program, but you get a semi-definite because density matrices have a positive semi-definiteness constraint. And it's one of the nicest ones because you can, again, analytically. And what you get, I'm not going to do it here, is that the optimal probability of success is now not proportional to the L1 distance, but to the trace distance, which is in a precise sense the non-commutative version of the L1 norm. And the optimum also comes for free, and it actually depends on the difference of states. It's just a projector onto the positive range of the state difference. So this is a famous result. It goes back to Helstrom, who didn't prove it that way, the way that I proved it here. But I thought this is a convex optimization workshop, so get some convex optimization in there. Probability depends on the trace distance of the states, but the optimal measurements also depends on them. So in order to win this game perfectly for any state pair, you have to be able to implement arbitrary measurements, which is not realistic in practice. And then there was this nice twist, going back to Ambanis and Emerson, and later Matthews, Wiener, and Winter. What if we fix our measurement to an informationally complete measurement, but we are only allowed to do this measurement, and then vary over all pairs of states to see how good this fixed measurement is at distinguishing quantum states in the worst case. This is kind of a quality assignment for the measurement that you do, and you would expect that kind of if your measurement does well at this, then it should be a good measurement for quantum state tomography also. So this is a nice twist. But this is a bit difficult because a measurement is lossy. So if we map T operators to classical probability vectors, we inadvertently lose something. So by fixing the POVM beforehand, in the worst case, we cannot hope to achieve Helstrom's bound exactly. But we can still try to compare. And again, the quantum motivation is check how well a fixed experiment performs at distinguishing quantum states. And there's actually also a classical motivation that I thought I had come up with, but people at Caltech told me that this is a very relevant motivation. It also allows you to use a grid to approximate the PSD cone in a very, very specific setting, if your map from quantum states to classical probability distributions is sufficiently fine and good, then this will potentially allow you to replace any SDP with a linear program, which might be beneficial in practice. Yeah, but let's look at what we have to say about that. And of course, I spent almost the entire half of the talk to talk about stabilizer states. Yes? Well, no surprise. Stabilizer states themselves form a valid measurement. You just have to renormalize them accordingly. And now you can ask yourself, well, stabilizer states are pretty structured. I mean, there's a lot of them, but they are kind of almost classical. So how well does the collection of all stabilizer states actually fare at distinguishing two arbitrary quantum states? Well, here's a nice trick. Just for simplicity, let me rewrite the state difference, an arbitrary state difference, by x, so that I don't always have to write. And now, what do we have to do? Like, this is the L1 distance of the measurement outcomes I observe. Because this measurement POVM gets me from state space to probability vectors, and then the best thing I can do is to optimize, use my classical optimal strategy to optimize over the probability outcome vectors. So this is the object I'm interested in. And now I can write it out in terms of what it actually is. It's just d to the n, it's a normalization factor, times the sum over all the possible stabilizer states, and then the absolute value of the trace inner product between that measurement and difference. And now let's use a sneaky trick. Baines and Emerson. Well, if you look at this, this is actually the same as dimension times the expectation of the absolute value of this random variable. It's a scalar random variable over all stabilizer states. And voila, there's fundamental lower bounds. The expectation of the absolute value of any random variable, any real valued random variable, in terms second and fourth moments. And before, I told you on multiple occasions that we managed to nail down the first 4 moments of stabilizer states. So this also applies here. And our results, I kind of simplified it a bit. If you just consider pure states, then the cost you pay for any state pair is a factor of 1/6. So kind of you can never do better with a stabilizer measurement than the Helstrom bound of the trace distance, but you also don't do much worse. Okay, and with that, and I try to convince you today that random information about moments. This is just the fact, this hints much of our research project. And one idea to like somehow soften this, partially de-randomize existing proof techniques to get by with as few moments as possible. The fewer moments you need, the more stronger your randomized proof technique is. And then at the same time, we try to come up with like structured models that fit these desiderata. And we propose to sample only from group orbits, because this has structure and randomness. We focused completely on the Clifford group in stabilizer states. And representation theory actually allows you to compute these moments, not only for the Clifford group, but in general. And then, remember, we found this magic spot in 2016, and we got the optimal results. Unitary channel tomography with average gate fidelities, and this fun application of how to distinguish quantum states. Thank you.